Hey everybody, and welcome back. It's class 9. We're going to solve quadratics using square roots, but we're going to look for imaginary solutions and imaginary numbers. So this is going to be the first time that imaginary numbers are going to make an appearance in our lessons, and we no longer are saying there are no real solutions. We're going to start talking about imaginary solutions. So objectives for today, we're going to first go back to just real world quadratics. So a lot of projectile questions. So objects, when you throw them up in the air, will move in the shape of a quadratic, and then their height versus the time they're in the air will also be able to be mapped out using a quadratic function. We will then simplify negative radicals, so this will be the introduction of imaginary numbers, and then we'll do some solving with imaginary solutions, and we'll just take a look at what happens if an imaginary number is raised to a power. What do you do with that? Questions for today. When presented with the square root of a negative number, what are the steps to getting that imaginary solution? And if you have I raised to any power, where that power is a large whole number, what are the steps to determining the simplified value of the expression? So last class, we looked at finding and comparing the different characteristics of quadratics, so whether it was standard, vertex, or factored form, and then seeing, okay, how do we compare the two of those? So maybe with the max and mins, with the intercepts, with different rates of change from different intervals, making sure that you can do all that. And then we looked at factoring quadratics with a lead coefficient greater than 1. So that is the A value. If it is greater than 1, then we factor it using the box method or the window pane method. All right, projectile motion. So projectile is something that is thrown in the air, launched in the air, anything that basically goes in the air and gravity gets to act on it. So in these formulas, we are not accounting for drag, and drag is the friction caused by the air. So when you throw something in the air, if it has surface area, it is going to have drag. And that just means that the air acting against it is causing friction, which means it would not be a perfect parabola. So projectiles in an ideal environment, so no drag, would be a perfect parabola. When there is drag involved, it's a slightly more complicated equation. We're going to start basic and then you introduce drag later. So the two equations that we're going to look at are h of t is minus 16t squared plus v0t plus h0. This is essentially height versus time in feet. So the one is in feet and one is in meters. So the speed of gravity in feet per second is 32 feet per second. So in the formula, you divide it in half and it's acting against the object, so it's a negative force. So it will be minus 16 t squared. So that's our gravity. V0 is velocity upwards at time 0, so vertical velocity at time 0. And then h0 is the height of the object at time 0, so the starting height. The other one is meters per second. The speed of gravity in meters per second is 9.8. So in our formula, the force of gravity acting against it will be represented by minus 4.9. Now you do need to know both of these equations because a word problem will say object is launched into the air at 120 feet per second, starting height of 0. When does it hit the ground? And you will need to know, okay, if I'm doing feet per second, I need the minus 16 version. If it was 50 meters per second, I need the meters version. And this is based off the physics formula. Displacement is equal to ut plus a half at squared. So displacement is distance covered, u is initial velocity, v is final velocity, which v is not included in this one. These are known as the SUVAT or UVAST equations. So if you've taken a physics class, you're probably familiar with this. If you have not, welcome to basic physics. And then a half at squared, so a half times acceleration, which in our case is due to gravity, and then t squared is time. So we have t and t squared. So this is going to be used in our case to determine the height of an object. So the height versus time is going to look like a parabola, but this is not like, oh, that's the spot where it lands. This is really how long it takes to go up and come back down. So it could be an object going straight vertically up, down, or if it was something like a golf shot, we're talking about the vertical height, so the change in height as opposed to the change in distance. So if you drop a water balloon, how long does it take to fall 9 feet? So notice that it's in feet, so that means we're going to be using our feet per second formula. So that is height over time is equal to minus 16 t squared plus initial velocity times t plus h0. So at the moment, we're just saying you drop a water balloon, how long would it take it to fall 9 feet? So we don't really care about the starting height. We're just saying it's at whatever height it's at, and there's no initial velocity because you're dropping it, so you're not launching it into the air. So in both cases, these are disappearing. So we would say 9 feet, so minus 9 feet because it would be going down. 9 feet equals minus 16 t squared. And we need to figure out what time is. So we would divide by 16 on both sides, or by negative 16, I should say. Negatives cancel out, so they're both positive. So 9 over 16 equals t squared. Square root both sides. So square root and square cancel. When you square root a fraction, you can separate it as the square root of the top and square root of the bottom. If you didn't know that, now you know it. So a fraction inside a square root can be split into its square root on top and square root on bottom. Square root of 9 is 3, square root of 16 is 4. So it takes 3/4 of a second to fall 9 feet. All right, golfer tees off her golf shot from a height of 10 feet above the pin. So the pin is where the flag is. So if we were to, kind of imagine what this picture looks like, you've got the green, and you've got the hole, and there's a flag coming up out of it, which the golfer is aiming for. And then somewhere nearby, the golfer is like up here and swinging. And the ball goes up and then comes down. So we are trying to figure out, okay, difference in the height between the two is 10 feet. So the tee box, or where the golfer hits the initial shot, is about 10 feet higher than where the green is. And that's fairly typical in golf courses, so that the tee box is just a little bit higher than where the actual flag is, or the pin. The initial vertical speed of the ball. So when you go to hit the ball, it'll go up, start turning, come back down again. The speed would be the speed at which the ball actually travels, but we are talking about the vertical speed. So this is how fast the height changes, which is slightly slower than the actual speed of the ball. The speed of the ball is based off a horizontal speed and a vertical speed. So vertical is the one we were talking about because we were talking about the change in height over time. So change in height over time it's in feet, so minus 16 t squared. Initial vertical speed is 100, so 100 t, and starting height is plus 10. How long does it take for it to hit the ground? When it hits the ground, the height would be 0. So 0 equals minus 16 t squared plus 100 t plus 10. So in a lot of these word problems, we are going to solve either by graphing or by quadratic formula, because real world does not often work out nice and pretty. So if you are doing quadratic formula, you would sub in all those numbers. I'm just going to solve by graphing in this case because it says I can round to the nearest hundredth. So in my graphing calculator, I'm going to do y1 is equal to minus 16. Now I'm going to go back to x's because my calculator deals with x's, not t's, plus 100x plus 10. And then I like to do the y2 equals 0 and find where they intersect. So plug that in your calculator, minus 16x squared plus 100x plus 10, second line 0, hit graph, and try and find the actual solutions, and then come back and see, did you get it right? So I hit graph, I can see the quadratic go really high up, really high down. I can't see the top of it, but I don't really care. I can see where it hits the x-axis in both cases. So this is just a zoom standard screen. I go to second function trace. I want where it intersects because I have two lines. So first curve is y1, yes. Second curve is 0, yes. For the guess, at the moment my cursor is at 0, 0, so I'm just going to move it over to the right because I care about the point where it hits the ground, where it's coming back down. And that is at 6.348, and rounding to the nearest hundredth, so time is 6.35 seconds. All right, so your turn. Object launched at a height of, it's 19.6 meters per second from a 58.8 meter tall platform. The equation for the object's height at time t is h of t is minus 4.9 t squared, so this is a meters one, plus 19.6, that's our initial height per sec, or initial speed, and 58.8 is that h of 0, the initial starting height. When does the object strike the ground? So when is the height going to be 0? So how long does it take for it to get back to the ground again? We're going to get two answers anytime you solve these quadratics. You get one that's a negative t, so that would mean like if we went back in time, this is where it would have been on the ground. So that's an answer we just negate. It's not possible, we don't use it. We want the t that is positive. So forward in time, when is it going to hit the ground? Second one, object is launched directly upwards at 64 feet per second. Platform 80 feet high. What is the max height and when will it attain this height? So this time we're looking for the max of the function. So again, in your calculator, looking for that max point, or in Desmos you could do it, or if you want to put it into a quadratic and try and find that h value, you can certainly do that. An object launched from ground level directly upwards, 39.2 meters per second. For how long is the object at or above a height of 34.3, and what is the minimum of h of x? So two things. When is it between, or at what points, at what times is it at a height of 34.3 meters or above that, and what is the minimum of the function? Pause the video, come back and see how you did. So for the first one, I just typed in my calculator. Remember, x's instead of t's. Second function trace, find out where it intersects the line y equals 0, and I get x equals 6. So at 6 seconds, so time equals 6 seconds is when it's going to hit the ground. For the second one, we have to actually write our equation as well. So the height over time, this one is feet per second, so we're back to that equation, minus 16 t squared. Initial speed is 64, so 64 t. And what will the max height, plus 80 feet starting height. And then we're being asked for the max. So this one I did on the Desmos app on my phone, just because it's a great one for finding max. You could also do it by completing the square, since 16 and 64 are both divisible by 16, so you could do it that way if you chose. All right, so what I ended up getting was at 2 seconds, so at t equals 2, the max height is 144, so this is the max. If you're doing it in your calculator, you would type it in, x's instead of t's, and you would do second trace and you would use the maximum feature. It'll ask you two questions. It'll ask you left bound, which means you put the cursor, so if you've got your quadratic going up, you put the cursor to the left of it, hit enter. Your right bound, same thing again, but you move the cursor over to the right, and then you hit guess. It'll find the highest point between those two bounds, which is the vertex. Third one, object launched from the ground directly upwards. For how long is the object at or above a height of 34.3? So we've got h of t it is meters per second, so minus 4.9 t squared plus 39.2 t, and then it's launched from the ground, so h of 0 is just 0. And then we want to know when is that at a height of 34.3 or higher. So we want to know when is the height 34.3. We'll get two values of t, so between those two. And then for how long, you're going to say, okay, what's the distance between those two? So when I put that in, I used Desmos again. I put the graph in, I did another one for y equals 34.3, and it ended up being, let's see, 0.3. So between 1 second and 7 seconds. So from t equals 1 to t equals 7, it was above a height of 34.3, so we would say for a total of 6 seconds, it was over that height. I think this is a typo, actually, minimum, because the minimum is negative infinity, since it's going up. Or lies, minimum, in real world, 0, because it's going to hit the ground. So that would be all I could think of. I think I just had a typo in here. I probably didn't erase the old question. Okay, so now we are going to introduce the idea of radical, negative radicals, which is going to result in imaginary solutions. So this is the first time we've introduced imaginary numbers, and a great site I saw was kind of explaining why we have imaginary numbers, and it was a case of like, all right, when we first started, we were dealing with just whole numbers, but then we realized, oh, you know what, we need negative numbers to make the math work and to make situations in our world make sense. And then we realized, oh, you know what, we need fractions, we need decimals. And then, oh, we need radical numbers. Actually, we need irrational numbers now too. So we need something like the square root of 2. It keeps coming up, or pi. And imaginary numbers was just the next set of numbers we needed. So the name of them is a little bit off-putting, because it's like, oh, imaginary, like what? That just seems like total fabrication versus like a irrational number. Like irrational, also kind of a weird name for a number, but it is a useful number when it comes to mathematics and solving certain types of equations. Imaginary numbers, same thing, is a set of numbers that is going to be used to solve particular types of equations. A lot of sound and electric problems, so like a lot of engineers will use imaginary numbers to do a lot of their problem solving that comes up in day-to-day business. So a couple of rules you're going to need. If you have the square root of -1, it is equal to I, 1i, so I being an imaginary number. So a single unit of imaginary number. If you square an I, so think about -1 squared, the square and the square root cancel, the answer is -1. If you cube a -1, or you have an I cubed, the answer will be -I, because you think about I squared is -1, so you'd have a -1 times an I to the power of 1, so you get -I, or minus square root of -1. And then I to the power of 4, well, think about that as -1. So I squared is -1, and another I squared is -1. Multiply them together, you get +1. So you could think of, I to the power of 4 as I squared times I squared, which is -1 times -1. So that's how we get that +1. So the questions we're going to get are simplify radicals that have negatives in them and then solve as well. The steps for doing this is when you have the square root of a negative number, you separate that into the factors of the number itself times square root of -1. So you take that negative factor out. So the square root of 49 is 7, and then the square root of -1 is I. So this would be equal to plus or minus 7i. Square root of -80, so root 80 times root -1. Square root of 80 is not a square number, so we're going to have to figure out the factors. So we got 4 times 20, but 20 is also factored by 4, so that means 16 is a factor. So 16 times 5, so 16 is my largest square number. So it'd be root 16 times root 5 times I, and that would be 4 root 5 I. and again, plus or minus. So the i's, like, it's an odd thing to throw in here, but the rules are pretty straightforward, and like how you solve it down is not super complicated. It's just pull out that factor of -1, that's your I, and then you simplify the square root just like you would in a normal scenario. So if we solve the equation, x squared plus 10 equals -15, if I subtract 10 from both sides, I get x squared equals -25, square root both sides, so I get x is equal to square root of -25, so that's square root of 25 times square root of -1, so it's going to be 5i, so it's going to be plus or minus 5i. The next one, we've got it in vertex form, so solve it down, -11 on both sides, x minus 2 squared is equal to -4, square root both sides, x minus 2 is equal to, so -4, so that's going to be 4 times root -1, so we're going to have plus or minus 2i. So then add 2 to both sides, x is equal to 2 plus or minus 2i. And this is going to result in a complex number. So we're going to have 2 plus 2i. They cannot be combined. So it's like 2 plus 2x, like the I. So there's 2 times this imaginary part. So that's an imaginary part of our number. And then the first 2 is a real part. They cannot be combined. And then the other one is 2 minus 2i. All right, solve each of the following. So you have x squared equals -112, x plus 19 equals 3, and 3 times x minus 1 squared plus 5 equals -103. Pause the video, try and solve each of them, simplifying all of your radicals down to include i's and simplest radical form. All right, let's take a look. So x squared equals -112, so x is equal to the square root of -112, and that is the same as root 112 times root -1. Square root of 112, so we're looking for a square number that will go into 112. So I'm going to start testing. 112 divided by 36, nope. 112 divided by, I'm not even going to test 25 because I know 25 doesn't go into it, so 16, yes. So I've got root 112 is root 16 times root 7 times I. So my answer is x is equal to plus or minus 6 root 7 I. Next one, x squared is equal to, subtract 19 from both sides, so -16. Square root of -16, x is equal to plus or minus 4i. And the last one, -5 on both sides. So 3x minus 1 squared is equal to -108. Divide both sides by 3. So x minus 1 squared is equal to 108 divided by 3. It's 36. So -36. And then square root both sides. X minus 1 is equal to, square root of 36 is 6. It's a -36, so it's going to be plus or minus 6i. And then we're going to add 1 to both sides. So our two solutions, x is equal to 1 plus 6i, x is equal to 1 minus 6i. So in our complex number, you have the real part, which is 1. You have the imaginary part, which is anything that contains i's, and then the overall thing, so the whole thing is called a complex number. So a solution can be complex because it contains real and imaginary parts. All right, so just simplifying these different values of I. Essentially what you can do, so if you have I to the power of 5, your options are, it's either going to be square root of minus 1, so just I, so that's I to the power of 1. It could be minus 1 if we have, it simplifies down to I squared. If it is I to the power of 3, it's going to be minus I, or minus square root of negative 1, and I to the power of 4 is 1. So since I to the power of 4 is 1, we can rewrite I to the power of 5 as I to the power of 4 times I to the power of 1. So remember laws of exponents, that would be I to the power of 4 plus 1, which is I to the power of 5. I to the power of 4 is 1, so it's just 1 times I to the power of negative 1. Or sorry, I to the power of 1, not negative 1. I'm getting confused by my little dot there. I to the power of 1 is just I. So this would be simplified down to be just a positive I, or square root of negative 1. I would take either one. I to the power of 22. So how many I to the power of 4s can you subtract out of this, and what's the remainder? So that would be I to the power of 4, and there's 5 of those. So like if I take 22, 22 is 4 times 5 plus a remainder of 2. So I could take out 5 multiples of I to the power of 4, and I'm left with I to the power of 2, which is just minus 1. I to the power of 227. So we know 200 is divisible by 4, 220 is divisible by 4, so 224 is divisible by 4, which means there would be a remainder of 3. So this would be I to the power of 3 left over, which is negative I. So that's the one up here. And then 300 is divisible by 4. That would be 25 times 4 is 100, so 25 times 12 is 300. So this would just be 1. It would divide down by 4 the entire way. So we're thinking of this as like I to the power of 4 times I to the power of 4 times I to the power of 4, and you would write that down, what did I say, 12 times? So each of these is 1 times 1 times 1. That's why our final answer is just 1. So we're simplifying it down. So looking for how many times you can take I to the power of 4 out of it. So subtract it out, and then what's the remainder? That's your goal. If you had something like I to the power of minus 6, well, you can add 4 to it. So that would be I to the power of minus 2, add another one. That would be I to the power of 2. And I to the power of 2 is minus 1. Sorry, no. So it'd be, oh, it is minus I, never mind. My bad. I squared is minus 1. Done. I'm overthinking it here. Getting too far ahead of myself. So if you come across that, like i's up to the very high power, all you have to do is just subtract out 4 as many times as you can, or add 4 until you get a positive exponent, and then the remainder is what you go up to your table for. So, okay, what is that remainder simplified? Central questions for today. When presented with the square root of a negative number, what are the steps to determine the imaginary solution? You square root of the negative number, you take square root of negative 1 times square root of that positive value, and then you simplify the positive value and put an I after it. Presented with I to the power of a, you subtract 4 out from the exponent as many times as you can until you're left with a remainder between 0 and 3, and then you evaluate that. If it's a negative exponent, you add 4 until you're left with a exponent of something between 1 and 3, and then just evaluate again. After lesson, you should be able to complete the Module 2 folder, Solving by Square Roots and Imaginary Numbers. So complete the discussion and the independent practice.